I'm Jussi Jokinen from University of Jyväskylä. Today to answer your questions after the presentation is my co-author Tuomo Kujala. One of the big selling points of advanced driving assistance systems, or ADAS, is that the drivers can spend time with non-driving related activities. This is of course fine as long as the system works reliably in all driving conditions, but it is critical for safety that the driver is able to supervise the system's performance and take over control when the situation so requires. Unfortunately, as we all know, humans are poor at detecting automation failures. Moreover, this detection rate is not constant, but depends on various factors related to the user, the task environment, and the automation. For instance, as shown here in this figure, detection rate of automation failure depends on how variable the reliability of the automation is. In other words, humans adapt their behavior to automation. Our work focuses on this adaptive capacity that humans exhibit when using automation. We ask, how do human drivers adapt their driving behavior to the presence of driving automation? Our approach is based on the theory of computational rationality. The idea is that humans rationally adapt to the constraints of the task environment and their own cognition by estimating the value of alternative action sequences and selecting those that maximize the expected long-term value. I'll explain the theoretical approach using the context of multitasking while driving. Let's assume a simple task where the driver's goal is to keep the car within the lane. Negative value is received from steering off the road. There is also a secondary task where the driver must visual search items in the in-car screen. Positive value is received from finding the desired item. Now there is obviously a resource conflict because both the safe driving and the in-car visual search require visual attention. In the context of this example, computational rationality stipulates that the driver's task interleaving adapts to the demands of both tasks. The goal is to maximize the joint task gain from these two tasks. In other words, the driver attempts to adapt a behavior that results in successful completion of the in-car search task while still driving safely. More technically, we implement our theoretical assumption using hierarchical reinforcement learning. I won't go into details now, but the computational model is based on an earlier work by us published in Human Factors. You can check out that paper as well as the conference paper for the full details of the implementation. On the general overview, we use reinforcement learning to derive what are called optimal policies, that is, sequences of actions that maximize expected value. These policies are of course discovered within the bounds of the environment and the cognition. Our idea is that there are separate models for the driving and visual search tasks and one more model that we call supervisor, whose task it is to decide how to allocate visual attention between the tasks. The subtask models attempt to maximize their expected value, but of course when they cannot use vision, they don't necessarily do a very good job at that. A critical point that we want to make is that they are still rational in that they follow an optimal policy. It's just that, for instance, when the model that does driving cannot see the road, it will have difficulties keeping the car on the correct lane. The supervisor's goal is to maximize the joint task gain. Because the driving task receives negative value only when the car is outside of the lane boundaries, and because the visual search task receives positive value only when the search task is complete, the supervisor will attempt to follow a policy that keeps the negative value from the driving task minimal while maximizing the positive value from the search task. By changing the conditions of driving and the search task, different task interleaving policies emerge from our computational model. For using our model to simulate how drivers adapt to automation, we implemented a simple lane assist in our model. It simply keeps the car from swaying off the road. As a result, the driving task will at no point yield negative rewards. which means that the supervisor learns a policy where it does not really needs to visually attend to the driving task and instead can focus on maximizing the gain from the in-car search task. This is a model of a driver who has adapted to overly rely on automation. We then turn off the lane assist to generate a prediction of what would happen when the assistance suddenly stops working. Below we show a comparison between a model that has adapted to the presence of the lane assist to a model that does not have this adaptation. Furthermore, we vary the amount of elements in the in-car search task to show that the design of the in-car interface impacts adaptation. Before showing the results, we want to emphasize that these are crude simulations only, aimed at showcasing our theoretical approach, not for making actual design choices. While the original human factors paper has human data from a driving simulator to validate the model, here we only present theoretical predictions. Shown here are the predictions of our model for in-car glance duration, that is, how long on average the supervisor conducts the in-car visual search task before returning eyes to the road. First, we see that as the number of UI elements increases, the model predicts that drivers make longer in-car glances. Furthermore, we see that the model with lane assist on, represented by the blue boxes, has adapted to this feature by generally having somewhat longer in-car glance durations. Here are the results for the model of in-car glances in one task. This is the number of times that the model on average initiates the search task before the task is completed. We can see that for the model that has adapted to the lane assist, again shown in blue, there are fewer glances. This is balanced by on the average longer glances that we saw in the previous figure. Finally, this adaptation of task interleaving is visible in driving safety. Here the blue model that has adapted to the lane assist has a clearly larger probability of deviating from the lane. This is understandable. The model has adapted a task interleaving policy that does not value highly the return to the driving task before the search task is completed. As a result, when the lane assist stops working, this adaptation results in risky behavior. The predictions of this paper, even if not validated against human data, demonstrate the utility of the computational rationality approach for modeling human adaptation to driving automation. The important message is that predicting how humans adapt their goal-oriented behavior to changes in the task environment is far from trivial. This is due to the extraordinarily complicated interaction between dynamic task environments and rational action selection, which is bounded in multiple ways. In our computational experiments, these bounds include imperfect knowledge about the status of the driving task and limited visual acuity, resulting in having to share attention between the driving task and the in-car search task. By defining these and other bounds in detail and in a psychologically justified way, it is possible to emerge the behavior. This adaptation should always be considered when designing new driving technologies. Thank you.